dot k 5 6, that is equal to k square plus 5k plus 6 is equal to 0. Okay, now solve these equations. You will get two factors, k plus 2 is equal k plus 2 and k plus 3 is equal to 0. So k is equal to minus 2 and k is equal to minus 3. So here is the complete this question. For what is our question? For what values of k these two vectors are orthogonal? So this is the answer, that for minus 2 and minus 3, the value of k, if minus 2 and minus 3, these two vectors are orthogonal to each other, right? So that is our answer. So this question asking 2 marks. Let's solve next question, question 1b, second part. This question asking 3 marks. Find the standard matrix for the linear operators on R2 with rotation of 90 followed by reflection about the line y is equal to x. About the line y is equal to x. So here we have to find the standard matrix for the linear operator on R2 with rotation of 90 followed by the reflection about the line y is equal to x. So first of all we have to find the standard matrix for the rotation. So the rotation of a vector x is equal to x1 x2 through angle theta is equal to 90 about the origin is given by the operator with this matrix A1. A1 is cos 90 minus sin 90, sin 90 cos 90, that is equal to 0 minus 1 1 0. Okay, so this is standard matrix for the rotation with angle theta is equal to 90. And now we want to find the standard matrix for the reflection about the line y is equal to x, and then we have to multiply of this two vector, this two matrix, 2 cross 2 matrix. Okay, so let's try to find the reflection in the line y is equal to x is given by the operator A2 is equal to 0 1 1 0. So that's why the rotation of a vector x is equal to x1 x2 of 90 followed by reflection about the line y is equal to x is given by the linear operator A is equal to A2 into A1 equal to 0 1 1 0 into 0 minus 1 1 0. That product of that two matrix, 2 cross 2 matrix is equal to 1 0 0 minus 1. Okay, 1 0 0 minus 1. So this question is complete now. Next question, question 1b, third part. Show that the function t from R2 to R2 given by the formula t of x1 x2 equal to x1 plus 2x2 3x1 minus x2 is a linear operator. Okay, show that the function t from R2 to R2 given by the formula t of x1 x2 is equal to x1 plus 2x2 3x1 minus x2 is a linear operator. This question asking 2 marks. So to prove that linear operator, now operator, why here use operator? Because domain and codomain are same, so that's why here use operator word. Otherwise we use linear transformation. Okay, but exactly the linear transformation can be say that linear operator if our domain and codomain are same, right? So here domain and codomain both are R2, so that's why we use linear operator, this word linear operator. Now to prove that transformation is linear, what we have to prove? That two conditions there. First condition is t of x plus y, that is equal to t of x plus t of y, and second condition is t of alpha into x, that is equal to alpha into t of y. If we prove these two conditions for any vector x and y belongs to the domain, then we can say that transformation t is linear. Okay, so exactly we try to prove that two conditions, that t of x plus y is equal to t of x plus t of y, and next is t of alpha into x, that is equal to alpha into t of x. So let x is equal to x1 x2 and y is equal to y1 y2. So x plus y is equal to x1 plus y1, x2 plus y2. Now t of x plus y, we find t of x plus y. T of x plus y, that is already we defined x plus y, that is x1 plus y1, x2 plus y2. So t of x plus y can be written as t of x1 plus y1 comma x2 plus y2. Now we use the definition of transformation, which is already given, that t of x1 x2 is equal to x1 plus 2 x2 3x1 minus x2. So try to understand that definition with this logic, that t of x1 x2, now x1 is first coordinate, x2 is second coordinate, right? So you have to understand that t of x1 x2, that is equal to first coordinate plus 2 into second coordinate comma 3 into first coordinate minus second coordinate, right? So now you can understand how we define t of x1 plus y1, x2 plus y2, that is equal to first coordinate plus 2 into second coordinate, right? So first coordinate is x1 plus y1 and second coordinate is x2 plus y2. So x1 plus y1 plus 2 into x2 plus y2, then comma 3 into first coordinate, that is 3 into x1 plus y1 minus second coordinate, that is x2 plus y2. Okay, so that can be expressed as x1 plus 2x2 plus y1 plus 2y2 comma 3x1 minus x2 plus 3y1 minus y2. Okay, so this question is this first condition we satisfied, that t of x plus y is equal to, okay, now we want to find t of x plus t of y. This is first equation. Try to prove t of x plus t of y. So t of x plus t of y is equal to t of x1 x2 plus t of y1 y2, that is equal to x1 plus 2x2 y1 plus y1 plus 2y2 comma 3x1 minus x2 plus 3y1 minus y2. Second equation. So by 1 and 2 we get t of x plus y, that is equal to t of x plus t of y. So third equations. So from 1 and 2 you can see that t of x plus y, that is equal to t of x plus t of y. Okay, now try to prove second condition of the linear transformation, that is t of alpha x is equal to alpha into t of x. So t of alpha x is equal to t of alpha into x1 x2, where alpha belongs to R real numbers, that is equal to t of alpha x1 comma alpha x2, that is equal to, use the definition of t, first coordinate plus 2 into second coordinate, so that is alpha x1 plus 2 into alpha x2, then third into first coordinate, that is 3 into alpha x1 minus second coordinate, that is alpha x2. Now alpha can be you can put outside from the bracket, so alpha into x1 plus 2x2 comma 3x1 minus x2, and that is exactly the t of x. So alpha, that is equal to alpha into t of x. So we prove simply that t of alpha x is equal to alpha into t of x. Okay, now both the conditions are satisfied here, so this transformation t is linear. Okay, we can say that this transformation t is linear by 3 and 4. Now using some another method you can also check that transformation t is linear or not. You can see here is the definition, t of x1 x2 is equal to x1 plus 2x2 3x1 minus x2. So first and second coordinate both are linear. Okay, first coordinate is x1 plus 2x2 which is linear, and second coordinate is also 3x1 minus x2 which is linear. So this property, this condition we only use for Euclidean linear transformation. That means whenever t from Rn to Rm, we can use directly, we can directly say that the given transformation is linear or not. Okay, in fact you don't need to check that these two conditions if you try to understand very properly for Euclidean linear transformation. But t from Rn to Rm, the first coordinate is linear, x1 plus 2x2. Why it is linear? Because it can be expressed as linear combination of x1 and x2. Simply the first coordinate x1 plus 2x2 is linear because of it can be expressed as linear combination of x1 and x2. Similarly, you can see second coordinate 3x1 minus x2, which is also linear because also that can be expressed as linear combination of x1 and x2. So directly you can say that the given transformation is linear because the first and second coordinate both are linear. Okay, you don't need to check that these two conditions, but our definition for linear transformation is t from v to w is linear if these two conditions are satisfied, that is t of x plus y is equal to t of x plus t of y and t of alpha x is equal to alpha into t of x, and these two conditions are satisfied for any linear any transformation. Okay, so for general transformation, to prove that that transformation is linear, we have to use these two properties, these two conditions. But for Euclidean inner product, you can just write down that first and second coordinate are linear, so this transformation is linear. That is enough for this question. Okay, so let's try to check next question. Question 2, first part. This question is important question. It's a question of vector space, the chapter of vector space. We prove that the given set is a vector space under this addition and scalar multiplication. That is our question. So just read properly and try to understand what is the question. Question 2, first part. Let V be a set of positive real numbers. Set of positive real numbers, that means R plus. Okay, with addition and scalar multiplication, defined as x plus y is equal to x into y. How we define addition? X plus y is equal to x into y and c into x is equal to x raised to c. Show that V is a vector space under this vector addition and scalar multiplication, that we have to prove. So we don't need we prove that the given set is a vector space using this addition and scalar multiplication. That addition means x plus y is equal to x into y and c into x is equal to x raised to c. Okay. Solution. So what is to prove vector space, the given set is a vector space, what we have to prove? We prove all the 10 conditions. The 5 conditions is for are for addition and the another 5 conditions are for scalar multiplication. Okay, in 5 conditions there are closedness, commutative, associativity, existence of identity, existence of inverse. That 5 conditions are for addition and another 5 conditions for scalar multiplication, which is closedness. Second condition is associativity in multiplication, then distributive law, 2 are distributive law, and last one is uniqueness. Okay, identity 1. So here is a question, again I repeat the question, that let V be a set of positive real numbers with addition and scalar multiplication defined as x plus y is equal to x into y and c into x is equal to x raised to c. So one by one we try to prove all the 10 conditions, right, for this set. First of all, closedness. Now x plus y is equal to x into y, that is belongs to V. Why that is belongs to V? Because you can see any two positive real number, take any two positive real number and then multiply, that is always positive. That means since multiplication of two positive real numbers is always positive, so that's why x plus y, that is equal to x into y, belongs to V, where V is a set of positive real numbers. Okay. Now commutativity, that means we have to prove x plus y is equal to y plus x. Okay, but what is x plus y? X plus y is equal to x into y, where x and y are positive real numbers. Now for x into y, that can be written as y into x. You know that 2 into 3, that is equal to 3 into 2. That conditions are there for real positive numbers, right? So x plus y, that is equal to x into y, that is equal to y into x, and y into x can be written as y plus x. So we prove x plus y is equal to y plus x. So first two conditions are satisfied for addition. Okay. Next condition, third condition, associativity of addition. For x, y, z belongs to V, what we have to prove? X plus in bracket y plus z, that is equal to in bracket x plus y plus z, that we have to prove, right? So x plus in bracket y plus z, that can be written as, that is equal to x plus, now y plus z can be written as y into z, so x plus y into z, that is equal to, now x is a positive real number, y into z is also positive real number, so we define x plus y into z, that can be written as x into y into z using the definition of addition. Now x into y into z can be written as in bracket x into y into z, that can be written as x into y, that can be written as x plus y in bracket x plus y into z, and that is equal to x plus y plus z. So you can see in each and every step there is some reason. Okay, without reason we cannot write any step. For each and every step here there is some special reason for that, behind that. Okay, so just try to understand that reason. Okay, so this condition is also satisfied, associative of addition. Now next we have to find identity element. Identity element, we have to find existence of identity element. Now x plus 1, now what is our identity element? Call it 1. Okay, just try to assume that 1 is our identity element. So x plus 1 is equal to, now x plus 1 can be defined as x into 1, that is equal to x. Similarly you can prove that 1 plus x is also x. So 1 is the identity element for the addition in vector space V, in this vector space V, that 1 is our identity element for this vector space V. Okay, so fourth condition is also satisfied. Now fifth condition, inverse, we have to find inverse for any positive real number x. Now what is it? Inverse for any positive real number x, existence of additive inverse. For any x belongs to V, there exists 1 upon x belongs to V. Why 1 upon x belongs to V? Because x is a positive real number. So for any positive